Or you, oh, I just keep talking. Forgot to turn on the mic. All right, guys. Sorry. All right. It's been like weird 1 minute there of talking. All right. Okay. Let's start over again. So what we are going to do now is just to apply the calculus technique to the this different kind of the charge distribution. Okay. All right. So what you have right now is you have a ring of radius A carries a uniformly distributed positive charge, which is total amount of charge is capital Q. Okay. And calculates the electric field due to this ring of charge at point P, lying at a distance x away from the center and along the central axis perpendicular to the plane of the ring as shown in the figure here. Okay. All right, guys. So of course, because the charge is continuously distributed, so what you have to do is you have to pretty much slice this charge into a tiny piece of charge yourself. So what we did before was just like we do the slicing here, and we say that, okay, within that slice, it contains a tiny amount of charge in there. So we can say it's like a dq. That dq is approaching zero. It's super, super small. All right. And from that dq charge, what you can tell right away is, all right, you focus on what is going on at point P. So I'm just draw a line of sight for you here. All right. So that's a radial direction there. So due to this dq, you are generating a tiny amount of charge. So let me highlight this one in red right there, just on top of that one. Okay, so that is a tiny electric field. Because the charge is tiny, so we say the electric field is supposed to be pretty tiny as well. So that's why we name it dE. It's a differential E. And from Coulomb's law, you can find the magnitude of that dE by saying that it's going to be K times the charge generating the fields divided by the distance from dq to point P. And from the Pythagorean theorem, you can say the R, the distance over there, is just the square root a squared plus x squared. Cool? All right, but we're just going to write it out as R for now. So it's going to be R squared. And that's it. So that's no big deal if you're just considering a single dq that you slice off from the ring. Now, what you want to do next is, of course, you keep doing this. So you're going to pick the next slice and you do that dq calculation. I'm sorry, you pick that dq and then generate the dE. You do the dE calculation, and then you move on to the next slice, next one, next. So as you can see, when you do the slicing around the ring, each piece of that dq that you are considering will generate a tiny electric field along with it. You guys with me? For example, let me pick the easy one for you to spot. If I move to the opposite ends of this one dq here, this dq here will also generate an electric field at point P in that particular radial direction, okay? And what you get, of course, from that tiny piece of dq, you're going to get electric field pointing in that direction. You guys with me? All right, let me pick another location of the dq on the ring. You might be looking at this dq over here in the front. Yeah, let me do that tiny slice there. So that's dq, the green one. The green one will also generate an electric field pointing, it's sort of like into the page a little bit. So you have to think in this like a 3D kind of way. Okay. And then you can just do every dq on the ring. But the whole point is this. My point is, okay, let me erase all those new stuff that I just added in. So while you're moving your dq that you're analyzing, you do dq, 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 right? Around the ring. It will generate the electric field dE. Okay, you start from the top, you generate dE over here. But as you move around, there will be dE, 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 dE. When you move around the ring, you guys with me? I'm doing like a mini animation over here. So that means each dE will just keep going. You get another dE, 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 until you complete the whole ring. So what are you getting at the end? You will eventually get those dE, like crazy amount of dE, but it will be in the shape of a cone. You guys with me? So those dE will be just that vector on the side surface of the cone. Cool? Can you imagine that? Yeah, sort of like that. So that would trace, I don't know, am I doing my perspective nicely or not? But okay, let me try to do my perspective. Mm, Try to make it nice. That's not bad. Okay, so this is what you get. You're gonna get all those vector on the surface of the cones. Cool. So that's it. That's it. So it means when you want the total electric field at point P, what you need to do is you need to sum all these vectors together. You just have to sum them all. Okay, those, you know, all those arrows there. How can you do that? The thing is, you do just like what you did before. Every time that you want to combine vectors together, you probably have some techniques like that you use, like you break into two components, the maybe the x-axis, the y-axis, or you in this case you can call it along the x-axis, and the other one is just perpendicular to that. So just go back to take a look at the red arrow over here one more time. Okay, so that means you can break this vector dE into two components. Okay, so one component is pointing along the x-axis, that's the dEx, and the other one is just perpendicular to it. So we have the perp side there, that side just saying that, hey, it's just perpendicular to the x-axis. So once you do that, you can just discard your original dE. Cool. So what you mean, what you're seeing over here is that means for other vector, for example, let me draw another one, the green, you can do the same thing. You can do the breaking into two components as well. So there will be dE along the x, and there will be a vertical components of that as well. So if you do all of this, the decomposition of the vector, every vector on the surface of this cone, the vertical components eventually will give you the whole vectors that will eventually paint the whole circular area perpendicular to the x-axis. You guys follow this? So that means in that particular direction there, so what you get from this decomposition of the vector is you getting crazy amount of this vector along the vertical direction here. See? Cool? Okay. And the good point about this one is this problem has a very symmetric setup. So as you can see, whatever you're seeing, you always have the opposite vectors pointing in every pair of the vector that you can pick. If you look at the one that's pointing up, there always one pointing down. Is the one pointing front, there will be the one that's pointing backward, on and on. So that means you can say that these components of the vectors, the vertical components, will eventually cancel themselves out. So you get nothing in the vertical directions. Cool? Does that make sense? Okay.
Okay.
And then the rest that you have left to add is just the x component of this. You have like a crazy amount of, there's so many of this, you know, all of that. I'll just write it down, sort of like give you a sense of what is going on along the x-axis. So that means what you really need is just you only need the dE along the x component. That's what you want. You want that component. You not want the whole thing. You just only, I want just a smaller here. Okay. So you just want the x components of the dE. Okay. So how much is that, Bajan? That's no big deal. What you got was just the original dE that you had. But then you look at this one, when you want just the x component, all you need is just doing the, okay, it's already dirty here. That's, it's just too thick. There you go. Let me rewrite this one again. All right. I don't need all those. I think you guys saw that one already. Here we go. So what you need for that is just that x component. So if you have that angle to be called theta, so you can name this one theta as well. So that means your x component of the dE is going to be just dE, and then you do the cosine theta. Cool? All right. And as you can see, you can do this dE cosine theta at every component. On every vector dE that you generated from the ring. This expression works. Okay. So what you need to sum is you just need to sum all this stuff together. That's all you need to sum. So that means what you are summing is just those, DE in the x direction there. All right, makes sense? All right, so what you need to add is just the x components of the DE. And once you're done with that, the final result, the electric field at point E, I can say total, is just going to be the integral of the DE along the x-axis, and that is going to be DE cosine theta, and that is going to be, I just substitute this DE here, so what you get is going to be K dq over r squared cosine theta, okay? And what kind of integral limit that you have to do? Well, Ajahn, I'm just going to have to circling around this. I'm just going to have to combine all the dq around the ring. So let me just put the ring here. So I'm just do the summation around this ring. Okay. And now let's perform the calculation of this integral, shall we? What is going to be the final integral of this one? Well, first, whatever constants that you see, you can pull it out from the integral. K is out. What else are constants? The R, what do you think about it? R. Is R constant? Well, yeah, then R is also constant. So I can pull R squared. What else? When you look carefully, but then the theta itself is also constant because wherever you look at this one, you have the same theta, right? Because that's just the apex. It's sort of like the angle at the tip of this cone over here. So actually cosine theta can be pulled out as well. Whoa. So what you have left to integrate is just the integral of the dq. And what is this?
Okay.
Cool. Well done. This is just the q. You just sum all those tiny bits of charge, dq. Once you sum around the ring, you're going to get back the whole total amount of charge on the ring. And that's it, guys. So your final answer is going to be K, capital Q, cosine theta, over r squared. And then of course, if you don't want to talk about this theta, because the theta is something that, I mean, you might want to re-express everything in terms of the x, the a, or whatever, then you can just substitute anything you like. The cosine theta is just the adjacent over hypotenuse there. So you can say it's going to be x over square root a squared plus x squared if you like. So that's good. And then divided by r squared, it's just a squared plus x squared. And that's it. You are done.
Okay.
Not bad. Okay, so it might look scary at first, but it's not. All right. So this is a very good exercise to do the vector analysis that it's in combination of calculus or the integral calculus here. And this is the part that I told you about. We're doing vector calculus, even though it's not like a full-fledged vector calculus. There are other tools that you need to use in vector calculus. But over here, because the quantity that you want to add is just vector quantities. So that's why we call this a vector calculus. But the good thing about this problem is you can just get away with doing the decomposition of the vector. And by symmetry of the problem, the vertical components of those DE just cancel out completely. So that's kind of nice. And then you only left with just components along the x-axis that you need to sum. So once you have only single direction to add, everything else just come down to just an algebraic integral. Okay, so I mean, toward the end of this calculation, the problem looks just like the previous problem. The DE that you got is only point along the x-axis. So the net electric field that you have to add is just going to be just numbers. Okay, so that's why that's sort of like the calculus part is already done, something like that. So not bad, is it? I don't know. It might has already been bad, but it's not that, maybe that's less than you were thinking. All right, now next one. All right, maybe next one is probably the peak of the whole business over here, because now we still have like a charge distribution along the, just like a piece of, like in this one, it's in a curve, but it's still like a single line of charge anyway. And then you would just need to figure out what is the net electric field. So let's take a look. So figure shows a plastic rod having a uniformly distributed charge Q, and it's negative. All right, so just to emphasize that we have a negative charge here. The rod has been bent in a 120 circular arc of radius R. That's fine. In terms of Q, the capital Q, and R, what is the electric field due to the rod at point P, guys? You want to give it a shot? Whew. No, that doesn't help, right? I've been doing this for months. All right. So you want to give it a shot? At least set up the first couple of lines of integration and see how can you sort of like start doing this problem. It's continuous charge distribution and you have an arc, okay? And you would like to figure out the electric field at point P. First thing first, you slice that charge into a tiny piece. So let me just do chop chop right there. So inside this one, it will contain the charge dq in it. Cool. And from this dq, you will get a little bit of electric field at point P. So let me do that drawing. Just try to draw a nice one here. So let me give you like some sort of like a radial direction here. Oop, what's wrong here? There you go. There, right? That's a radial direction. But because your charge right here is negative, you will get an electric field pointing towards it. So let me do the color code here. Oh, there you go. So electric field will point towards it. Make sense? Right there. Okay. And then what you need to do is just you have to just keep doing this. So you do another slice here. You're going to have electric field generated there. So let me put here. There you go. That's another DE there. And then you move on to the next slice. And then there will be another DE there. Another DE there. All the way. Just keep doing the DQ down to the bottom ends of this one. You're going to get the electric field pointing in this direction. Cool. So what I'm saying over here is when you keep doing that, you will generate DE here, here, all the way down to the bottom. Cool. So what you're getting, it turns out, is going to be the whole. Here, let me sort of like draw like an arc here. So you get tons of those vectors at point P. Yeah, these are vector of DE. And that's the whole thing over here. You need to sum them up. You want to do that vector summation of all these DE. Cool. All right. So that's the whole process there. So first thing first, what is the DE that you got from each individual DQ? But that's no big deal. The magnitude of the DE is going to be the K, the charge generating the field, the DQ, divided by the distance from the DQ to point P. And what is that? But that is just the radius of this arc. And they say that the radius of the arc is just R, so it's just R squared. Cool. And as you can see, this expression over here can be used for any DE. DE on top, that's fine. DE in the bottom, that's no big deal. I mean, you can use this expression for all the DE. So what you need is you want to do this vector summation, but you cannot just do this because this one is just the magnitude of your DE. You guys with me so far? Okay. So all of your DE right now over here having the same magnitude as this one. All right. They all K DQ over R squared, except the directions are all over the place. Well, it's not all over the place, but it's just the orientation is just spreading from the diagonal to what up there, and then you just come down according to that arc. How can you do this total summation there? We just do the same trick one more time. So what you're doing, you just break them into two components, one along the X and the other one along the Y. All right. The geometry of this problem is quite obvious. So what I'm going to show you here is just, okay, I'm just going to eliminate all this stuff over here just to be nice and clean. All right. I'm just going to delete those. All right. Let me just delete them all for now. All right. And I'm just going to bring back that DE, the first one that you saw. I can break this into two components. The one is vertical and the other one is, one is horizontal and the other one is vertical. So from there, I eliminate the original one and this is what I get. Cool. All right. And what you have over here is going to be DE along the x-axis and DE along the y-axis. All right. But if you look over here, all right, and let me do things symmetrically. Start from the top one. you are generating the electric field pointing upward, right? And then you do the same thing, right? You're going to do the component stuff. So you're going to break this into two components, up, X, okay, cool. And if you look at the opposite ends of this one, the one that's pointing towards the bottom ends of this arc, you do the same decomposition of the vector, horizontal, vertical. You notice something here? You have a symmetric setting. It's a mirror image above and below the x-axis. So that means you will always find its pair here. Look at the y component of the blue. It's exactly the same as the green components, the y components of the green, but they are pointing in the opposite direction. So as you can see, whatever you're looking at the upper part of this component, I mean the one that pointing up, there will always be a pair that is pointing down, opposite to that, always. So what I'm saying over here is you always be able to cancel the vertical component on every single EDE that you split out. So you get a complete cancellation on the vertical components. You guys with me so far? All right. So what you have over here is, okay, Ajan. So it means like all I need now is once again, just the X components of the DE that you need to do the summation. Does that make sense? All right. So that's what we are going to do there. So once again, well, Ajan, I don't want the whole thing. I only want the X component of this because we can say the Y components already completely cancel. So what you can say is net electric field along the Y is already zero. That's none along the Y axis. So it's just going to be once again your DE. And then now I have to do the components thing one more time. So look back here. Okay, I can name this angle theta if I want. Okay, so if you call that theta, all you need is just the cosine theta component of this one. So you take the magnitude of the DE, multiply by the cosine theta, you get the X components of the DE. Cool. All right, let me plug in all the thing. So what you want is you want to have those DX added. So you just sum them all. Yeah, you just sum them all. You want to sum from the top all the way to the bottom. So that's what you do the summation there. Once you're done with that summation, you're going to get the net electric field that is pointing along the x-axis. Cool. And then it's just, you just plug this thing into the, oh, way too far. There you go. Just plug it in here. So it's going to be integral of k dq over r square. And then they have a cosine theta in it. Almost. Well, I would say almost done. Actually, it's like 30% done at this point because you want to do the integral along the arc. You want to just have to complete the summation there from the top of the arc down to the bottom of the arc. Here comes the question. What's next? You might just say, about John, let's remove or pull out the constants from the integral, which is can be done there. K is good. K is constant. R, well, okay, John, the R is just always constant here. I can pull R squared out. What about theta? Not this time. The theta over here turns out to be your variable. You guys with me? Because you can see that from the top, your theta is up here, but down to the bottom, your theta is down here. So that means now your theta is a variable, something that is going to change. So you cannot take it out from the integral. So that's what you have left to do. The integral is just the dq cosine theta. Now here comes the question. What to do with this integral? It seems like you cannot avoid the integration in this problem now. When you say you're facing this kind of problem, does this remind you something here? Okay, let me rewrite this equation one more time. It's going to look like this. K over r squared and the integration of the cosine theta dq. This won't work. The reason it won't work because what you have to look, what you have to do is right now you're writing everything under the function of theta, but your integrating variable is now in the q, which doesn't seem to make sense, right? Because, well, not ready to do the integral in this form. You have to do some conversion first. So you have a choices. You either turn theta into q or you turn q into theta. to turn the theta into Q, that's kind of weird, right? Because then how can we take the angle turns into sort of like charge? That's kind of weird, right? So what we're going to do is we're just going to do the Q and turn it into something of theta. You already saw this once here. See, back in the day of the charge in a rod, on a rod here, you stuck with the dq, but you want to turn it into some sort of like a dx. So you have the linkage, right? The one that connects between the charge and the x, the position is just through the lambda. You just do the charge per unit length that allow you to connect the amount of charge and the distance along the x-axis. Yeah, very good. All right, so that's what we're going to do. The question is, how in this problem? How can you turn dq into something? I know the end games of this one, you want the d theta. If you can turn dq into something of d theta, then you do the integral under theta variable, and then you will be happy, right? So there are a couple of things that you need to know here. So let me, now I have to use more space here. So let me give you one more page here. Here we go. Guys, look at this. Now you have an arc. So it's sort of like it's an arc, huge arc over here. Okay. And you slice a tiny piece of dq here. This is like a zoom in thing. Arc length, very good, very good. It's getting there. So you already said there's a dq contained inside this one, but it's going to take up some space no matter what. So let me call the ds, because it's not along the x-axis or y-axis anymore. Let me call it like a distance, ds, something. Okay. But then if you remember the definition of the angle, well, then that's kind of like, remember, if you talk about the arc length in general, if this is the angle theta and this whole thing is your arc length here, an arc, and you have a radius over there. So everyone knows that the relationship between the subtaining angle theta is going to be the arc length divided by the radius, right? You guys with me with this? Okay, so it's going to be exactly the same with this tiny piece here and there. See that? So that tiny arc that you slice out that has a dq contained inside, it's going to take up a little bit of space there. So let me name this d theta. Does that make sense?
Okay.
So with that, now can you write out now what is going to be the relationship between the ds and the d theta? Well, then you just take it from here. It's the same formula. So the angle subtaining at the center is just going to be the arc length divided by radius. So at this point, you already got the ds is just r d theta. All right. But then, well, wait a second. It's not going to the dq just yet. You are only connecting between the arc length and the angle, right? So back to this. The way that you can connect between the charge and the length, you just have to go through the density. The charge density is the charge per unit length. So let's assume that you know that. Let's assume that the charge per unit length is lambda. So the good thing about this one is you can write down the connection between the ds and the dq just like before. You just say the amount of charge in there is going to be the lambda ds. You guys with me?
Okay.
But now you already knew that the ds is already can be written as an rd theta. So it's going to look like a lambda rd theta. And that's what you connect d theta back to dq. See, and once again, you utilize that lambda one more time. So that's why the density, even though now it's one dimensional, right? It's a 1D, the density. It's a charge per length, but it's allow you to convert between the amount of charge and the coordinates. So in the future, you might have to deal with the charge per unit area, maybe because your charge might be distributed across the area. Or next, you might have to face the charge density is per unit volume because you might put a charge in a tank or something like that, right? So that's why I just did the generalization of the words density. So the density doesn't need to be divided by volume anymore. It depends on the dimension of your problem. If you have only single dimension to talk about, your dimension is going to be one dimension, so it's going to be charge per length. If it's an area, it's going to be two dimension, it's going to be the charge per area. If your dimension is three, it's going to be charge per volume. But no matter what you're talking about, they are all density. Cool?
Okay.
All right, so I hope you sound like, okay, feel good with the word density now. It doesn't have to be divided by volume all the time. All right, so with this, now I know how to write dq as a function or as the variable d theta. Now I can just plug it back in here, guys. Cool. K over r squared integral of cosine theta. Now your dq is the lambda r d theta. Isn't that nice? Almost done, Mojan. Everything is nice and clean. You have a function of theta that you want to integrate, and your integrating variable is now theta. Now, the last thing that you have to sort of like be careful with is what is going to be your limit of integration, guys? What do you think? You don't need that. What limit of integration that you want to impose on this integral, guys? But from the look of the problem, Ajahn, yeah, I want to go from the top to the bottom. And because they said that the arc length sort of like bends in a 120 degree, so I know up here, it's supposed to be like 60 degree on top. It's break in half, and bottom, you can might just say negative 60. Does that make sense to you? But then you want to go from the top to the bottom, or you want to go from the bottom to the top. It's kind of like, okay, Dan, so what should we do? Okay, so the answer is this. You want to go from the lower value to the higher value all the time. Yeah, and that, right? There's some answer right here. That's very good. So you want to go from the bottom to the top. The reason for that is because of this. See, look at the arrow that I mentioned over here. Every time that we talk about this 60-degree angle below the x-axis, you don't seem, I mean, you seem to be agree with me that I need to put the negative sign over there. And when I sort of like talk about the top position over here, you agree with me that this is supposed to be positive 60 degree. Why is it so? Have you ever noticed why every time that you talk about the angle, it's the angle that measure with respect to the x-axis all the time and is measured in the counterclockwise direction? Have you ever had any doubt? Okay, the thing is, if you look at this figure over here, you have x pointing to your right side, y pointing up. My question is, where is your z-axis, guys? Where is the z-axis? The answer is you have to follow the right-handed system, right? If x point to your right, y pointing up, you just curl your forefinger from x to y, your thumb will point toward your face. So that means the z-axis is pointing to your face at this point. That's the z-axis. And you did this kind of analysis back in the day of when you did the circular motion or maybe the angular motion, angular frequency, all the stuff. You do the z-axis thing all the time. And that's what it is. You look at the right side. So if this is x, this is y, z is pointing to your face. And once again, if you put your thumb that is pointing to your face and the forefinger that's curling around, you can see that your forefinger is wrapping in the counterclockwise direction. So that's why I think that's correspond to what you learned before. When you go counterclockwise in this coordinate system, the right-handed coordinate system, that is your positive direction. That's your positive rotation there. So this is the reason why if you measure the angle counterclockwise, that is your positive angle. And if you do the measurement of the angle, but now you go opposite direction, that will be your negative theta. Cool? All right, so that's why everyone, I hope you agree with me that you're going to have to start from the bottom because that's when the value is lower. You want to start from the negative 60, or you can call it pi over 3 if you like in radian. And you're going to go the integral up to pi over 3. Cool. So that will be your limit of integration there. Isn't that nice? Okay, so I hope, I mean, even though it sounds like tedious explanation over here, but I think if you forgot about this coordinate system, so from time to time, when you actually solve some problems, there might be answers at the end that it just flip the sign and then you just confuse a bit. It's like everything is right, number is all correct. How come I get a negative value? I think maybe it's just the coordinate flipping, right? You just accidentally set the upper limit to the lower limit and lower limit to the upper limits, on and on. All right, so over here, now let's move on. So whatever constant I can pull out even more, and now R cancel. So let me cancel one of the R out. Okay, that's good. So the lambda is supposed to be constant in this one. So I pull lambda out as well. So only have left for you to integrate is just the cosine theta from negative 60 to positive 60 degree. And everyone knows the integral of cosine is just sine. So that's good. So now you have a sine theta here, and you do the limit from negative 60 to positive 60. And sine 60 is root 3 over 2. Sine of negative 60 is negative root 3 over 2. So that brackets over there will give you root 3. And as you can see, it's positive. It's kind of nice. So that's it. It's done.
Okay.
See, not too bad. They're not too bad. And the good thing is the final result give you only the x component of the net electric field. So if you want to rewrite everything in terms of the vector, you can say the net electric field, okay, at point P or at the center of the circle of the arc over here is just going to be that sigma EX that we just found out. And then you can just put I hat over there if you want. And that will be the answer of the whole thing in the vector format. Cool. All right. So I hope this showcase how or kind of like how deep can you go applying the calculus to the electric field calculations over here. And another thing is just give you like a quick like information that in the exam, the problem shouldn't go beyond this. All right. So I think this is good enough complexity. You see a little bit of complications, but it's not that bad. It's still within your, ability to manage using mathematics that you have already had. Plus, the settings still have some symmetry on it. So your calculation is not like super crazy that they have to do some weird integrals or weird limit of integrations. Okay. And the good thing is the integral is easy, right? You don't need like integration table or anything. So this is still within the range that you should be able to do. Okay, so let's consider this one as like an near the upper limit of the difficulty level that you're going to see in the exam, right? No more complicated problems than this one. Cool. All right, guys. So I think any questions so far? I hope by having seen these 3 examples, I think that's pretty much, I think you probably had enough already. Okay, guys, so I think this is a good place to stop over here because after this, we're going to move on to the next topic in electricity, which is electric potential, and that's in the next handout. All right, so just download the next one, and then we'll continue on that topics after the break. All right, guys, see you in 10 minutes. All right, so the next stuff that we're going to do here is electric potential. And with this completion of these topics over here, you will have every physical quantities related to electricity needed for everything else in whatever your life or your futures in scientific whatever thing. All right, so what we have over here is now I'm going to talk about today is the electric potential. The name is kind of like familiar because you have already done potential energy for gravitational fields already. And I will tell you right now, they are pretty much the same thing. All right. They're based on the same concept here. So we're going to pretty much redo everything here, but we're going to do it under electric fields. Okay. And so that's why along with that, eventually you are going to have a chance to take a look at potential energy, but for electric. So that is going to be electric potential energy. Okay. And next time, of course, you will have a chance to do like a deeper relationship between the fields that we have already discussed at length and the potential that we are about to introduce here. Cool. All right. So let's attack this one. But I'm mean, just like a quick warning over here, guys. There's going to be a lot of explanation from me today. The reason is because I think this is a good chance for you to go back and take a look at what does it mean by by potential energy. I don't know, have you done that before at the time of the potential energy calculations for Newtonian physics there, like the MGH and all this stuff, but I think you need it now. So that's my take on it. Okay, so if I ask you like a a very like a boring question, like, hey guys, what is potential energy? I don't know how would you answer this one in like a quick one sentence. But the whole idea is, if you want to talk about a formula, everyone should be able to sort of recognize that one. But Dan, I remember that it's an mgh in gravitational field. M is the mass, G is a gravitational acceleration, and H is just the height from a reference point or a reference height. So without talking about anything at all, actually I can do the same thing here. If I introduce to you, hey guys, I'm going to use electric potential energy. Can you guess what kind of equation that I'm going to get at the end? But of course, Ajahn, you have charge, right? Acts like a mass. You have E, the field that acts like G in gravity. And H, you can just call it like a distance or whatever displacements. So, and this is correct, guys.
Okay.
This is it. So this is supposed to be your sort of like final expression for calculating the electric potential energy in an electric field. However, where does this or this comes from? That's the question. Okay.
Okay.
So I'm trying to answer your questions right here. How did you get to the potential energy in the first place? So let me link back a little bit with the thermodynamics, shall we? All right. So it's kind of, are you serious? No, no, just a quick one. So if you remember the thermodynamics equation, the change of the internal energy equal to heat minus work. Right. We'll bring back some memory here. Yeah. But because right now we don't talk about heat anyway, so don't worry about that heat thing. There's no thermal effects here. But this equation is sort of like it was telling you that if this work done is the work done by the system, remember this? Okay, so what I can do is I can move negative sign to the other side. So what I'm getting at is going to be this. The work done from A to B is going to be the negative change of the internal energy. But we already discussed about this. Internal energy is that the total energy in your system. Even though back in the day of thermodynamics, we only care about the kinetic energy, but now you have, so all sorts of energy available to you. But the equation stays like this. The work done from A to B is just going to be the negative of the change of the energy of the system. So you guys agree with this equation now? My point is this. So now you can see that W that we're talking about over here is the W by the system. Every time that the system perform work, the energy of its system is going to get reduced. That's the whole key point of this equation. And that's the key point of the negative sign in the front. You guys with me here? Okay. So far, so good. Now, keep that in mind. So what I'm going to do is this. You guys familiar with this scenario all the time? I have, let's say, a mass here. And if I place it at the top of my screen and I let it go, bam. Everyone agree with me that at the top of the screen, the gravitational potential is high. Let me say the bottom of the screen, that's my reference. So that means it's like mgh up here. And once I let it go, it's go down to the floor over here, bottom of the screen, that's 0. So that means the top of the screen has a higher energy than the bottom, right? But once I let it go, bam, the potential energy is dropping, is decreased from the high value to 0 and I mean lower value. So it's a negative change, correct? But if I'm asking you about, hey guys, how much is the work done by the gravity? Of course, up top over here, the gravity is pulling this mass down right now. So once I let it go, bam, the work done is just the force multiplied by the displacement. Because now the mg is down and it's dragged this mass down. So gravity is doing a positive work. You guys with me? That's what it is. That's on the left. Gravity is doing a positive work. But what happens? You get a negative change in your internal energy, which is in this case, you only have potential energy. Does that make sense? So every time that gravity do the work by itself, the final effect will have the negative change in the energy of the system, and hence that negative sign there. So everything is just perfectly corresponds to what we learned from thermodynamics. Very nice and clean. Okay. Now, let's do that with the electric field, shall we, guys? Look at the figure on the right. Now, I'm having electric field pointing down. I have my charge originally placed at point A up top. So everyone know right away, this will have a force, electric force, acting on this equal to the charge of this multiplied by the field. So everyone with me now, see how easy it is for you to get from the field to the force multiplied by the charge. Now I let it go, bam, just like what we had with the mass. So the charge will just move from A to B, and it takes up the distance or displacement of D along the path over here, just straight downward. So I'm asking you, how much is the work done by the electric force? Ajan, that's easy. It's just the force times the displacement. And because right now the force is down, displacement is also down. So the amount of work done by the field, which is our system here, by the field is just Q E D, or you can say it's like a QDS cosine zero. Think of it that way. So it's a QE times D. See, recognize this? QED. There you go. That's what you got. Happy.
Okay.
All right, so far so good. So it's there. It's already there. That's not a big deal. But the problem is I want to link this one to the potential energy change. So it turns out what I'm going to get over here is just going to be equal to the negative, the change of the potential energy, right? But remember, every time that I see the delta, it's a final minus initial, right? So it's going to be the U at the bottom here at point B minus U at point A. So that means it's just going to be U at A minus U at B. And everyone agree with this. That means U at A has a higher potential than the U at B, high and low. So you can see that electric field is pointing down. This is exactly what you saw with the gravitational fields. When the gravitational acceleration is, of course, it's downward all the time. And when you are at the higher elevation over there, you say you have a higher potential energy. And when you lower yourself down, that's lower potential energy. So what I'm saying over here is, this is the definition of the potential energy. You guys with me?
Okay.
I mean, I discussed for so long just so you get to understand, like, hey, the work done by the field allow you to define the potential energy. And as you can see now, when you move along the field, see, the field is now downward. The field is downward. When you move along the field pointing towards the lower potential energy. Cool? All right. And here comes the thing, Mojan. When you keep saying that is the work done by the system, but this is gravitational field or this is electric fields, what is your system? What system you talking about? The answer is this, guys. Think of it this way. When you talk about the gravity, here, I'm down here. Start from the bottom. Okay. And I move it up. See, now I'm not gravity. I'm not earth. I'm not nothing. I'm just external force. So I come in and grab the mass and pull it up to the top of my screen. See, that is the work done by me. And I am not part of the system. I'm somebody else. What is the system? I just let it go. I just let go. I'm not in the picture anymore. So from the look of it, your system must be something that is playing between this pulling in. So what I'm suggesting you to think is, think of this mass having an invisible spring attached to the earth. Does that make sense? So think of it this way. Right now, this mass, there is an invisible spring attached to the earth. And what I'm doing, I'm coming from the outside, right? I'm external. I'm not part of the system. I'm pulling this mass and try to break them apart. So it's sort of like there's a spring and then I just stretch the spring. So see, now it's being stretched. And once I let it go, everything just snap back. Bam. It just snapped back down to the floor. So what is the system now? Is the earth and my mass right there, M. And my invisible spring is like that. And that's, well, it's not a spring, of course, it's a gravitational attraction, but that's the whole idea. So when I move things around, when it's up, it means the invisible spring is being stretched. So that's why you increase your your potential energy, because right now the spring is being stretched, right? It's ready to snap back all the time. Does that make sense?
Okay.
I don't know, does that help or not? So what I'm seeing over here is the same thing. Every time that you see the electric field, there must be some source of this field. We already discussed and calculated that. So that means there must be like, okay, Bajan, you have electric field pointing down. There must be like a big chunk of negative charge at the bottom, or maybe there's a big chunk of positive charge at the top to generate the field pointing down. So every time that there is a movement within that field, you are changing the configuration of the whole system, just like what you did with this, the earth and the mass. When you change the position, the configuration is changed. So that's why there is some potential energy change in your system. Cool?
Okay.
So I hope this helped a little bit, but my whole point of this one is that's the reason why you need the negative side, guys. That's actually, maybe that's the take on this whole thing. You need the negative side every time that you try to connect between the change of the potential energy and the work done by the system. You need that negative side. All right, there's a question comes in. Can potential energy be derived by Newton's law of universal gravitation, like gravitational? Yes, exactly the same. And you will see it too today in electric system. Yes, yes. All right, in a little bit. Yeah. So that's actually a very good question, and it will link directly to two types of the problems that you're going to face, okay, in general. All right, I'll loop back to your question in a little bit. Okay, so from here, once you understand where that negative sign is from, so you have to, so now you understand this equation over here. Okay, John, the work done, yeah, and now you have to, in your head, all the time, this is by the system, okay, not by external people over there. And if you would like to talk about external force, perform external work done, then you don't need the negative sign. I hope this is clear, okay? However, the reason that we emphasizing on this negative sign is because we want this, guys. We want the field to do its own work. So we will have the connection between the fields and the potential energy. So with this setup, now you can do the change in any direction, in any value, from A to B or A to C, wherever you want to go. So all you need to do, you just do the change, a tiny change at a time, and then do the final summation over there. All right. But all right, in general, we're probably not going to need the integration all the time, but at least this is a very official announcement of,
Okay.
this is the definition of the potential energy for going from A to B. Can be calculated from negative, now we understand where the negative sign is from, Q times E times displacement. Done. All right. However, there is still something else that you need to be able to make sure that you understand this. So let's move on to the next slide, guys. Okay. So in electric, it's kind of like inconvenience for you to talk about the charge all the time. Why? The reason is this. So over here, when we talk about mass, this mass is good. It's M, let's say mass M. I can grab this mass, take it to campus, bring it to you, borrow it, lend it back, whatever, and come back. It's still this mass M, correct? So everything is good. But imagine that you would like to do this with the charge, like an electron. And you say, but Ajahn, I'm going to lend you one electron tomorrow. Just bring me back the electron. Who would do that, right? The reason is because, well, based on quantum physics and all this stuff, like all electrons are indistinguishable. So you cannot even label the electrons. So let alone, well, You want to tag along with some electron, you cannot just trace one electron along. You don't even know which is which. You don't even know them. They all look the same. They are identical. So that's why what I'm saying over here is you cannot do the same business that you did with the mass. And you're going to use that thing with the charge because it's either too small or too many. You might have to deal with like Avogadro numbers of electrons, for example. So to be able to talk about the potential energy all the time is inconvenient, right? Because think of electricity in your house. If you want to say, I'm going to use electricity for the whole night, or you're going to use it for an hour, the amount of charge that is going to go through your maybe computer, your notebook, tablet, they're going to be different, right? So that's why introducing another term called electric potential.
Okay.
All right. And yeah, you're right. We just drop the word energy and that's it. You get another quantity in physics. We call it electric potential. That's it. Okay. So what it is, well, electric potential actually is just the electric potential energy. But then you do it per unit charge, guys. That's it. That's how simple it is. When you do it per unit charge, the good thing about this one is it's just like, okay, just do it per unit charge. And if you want to get back to the energy, you just multiply back the amount of charge that you want to do. So if I tell you what is the unit of this one, you will say, aha, right away. And that's what it is. The unit of this one is volt.
Okay.
Aha. No. No. Yeah, yeah. The reason is when you say households potential difference is 220 volts. I think everyone familiar with these numbers. This volt just give you an idea of just the potential difference, but it doesn't give you energy just yet. If you really want to know how much energy you are using, all you need to do is just multiply back the charge, because 220 volt is 220 joule per coulomb. And then if you want to spend like 5 coulombs, you just multiply 5 to the 220, so you could turn everything back into joule. Does that make sense now? All right, so actually you can actually come back to this equation that we define your potential energy, and all you need to do is just move this Q to your left-hand side. And that will be the energy change per unit charge. And whatever you have left on the right, we're going to define this as potential. And that's what it is, guys. That's it. So now we're going to name this using the V variable, the quantity here, we use a symbol V for potential. So the potential difference between 2 points is just going to be the energy difference, the potential energy difference between those 2 points divided by the charge. So that's it. The leftover is just this one. The nice thing about this one is, can you see? It's only relates the field directly to the potential. And you leave the business of the charge later. So this feeling was just like what you did with the force and the field. Remember that one? When you, John, let's do the field first. And once you want to get back to the force, multiply by the charge. Now we have the same kind of things that we can do here. If you want to talk about the energy, but John, let's attack the potential first. And once you're done with that, you just multiply by the Q, and then you will be able to find out what is the energy. Yeah. And usually every time you talk about potential energy, it's just going to be the change from one point to another point all the time. So that's why there must be a delta on it. But the idea is pretty much the same thing. There is a close connection between energy and just the potential, simply by multiplying by the charge. Cool. All right. So in conclusion, now we can talk about the potential without without worrying about what kind of charge is moving in there. So look at this one. If now you can see that, hey, that electric field is pointing down, you can say right away, this is going to be the high potential because it's upstream. Think of it that way. It's, you sort of like go against the field. And when you come down along the field, you are going toward the lower potential. See? So that's a nice thing about this one is once you look at the electric field lines, you can tell right away where should be the location of the high potential, where should be the location of the low potential by just considering the directions of the electric field lines. Okay? And just to check your understanding of everything that we have done so far, Look at this. Okay. Scenario are exactly the same between gravity and electric. No difference. Concepts are fine. If you have electric field pointing down, it's going to look exactly just like gravity at this pointing down. Okay. And good thing about this one is we already found out that here you have high U, this is low U, right? But then if you do it per unit charge, you get the V. We already got the formula for that. Delta U is Q E D. Yeah, the D is the distance between these 2 points. So all I have to do is just move the Q to the left-hand side, and it's the ED. See? You just take the E and the D, multiply, you get the change of the potential. That is it. That's it. Very good. Except now you have to know in your head that negative sign must be there all the time, guys. That's what it is. Oh, there's no negative sign there. Yeah. So the negative sign just to indicate that if you go along the field, you are going in the direction that the change is lower. It's going in a decreasing direction of the potential. Cool. All right. So the scenario will look exactly the same between gravity and electric system. All right. So as a question comes in here, potential difference and electric potential the same thing? Yeah. Yeah. Potential difference and electric potential. Wait, okay. I think what your question is asking is, I think the key is the word difference. So whenever you talk about the difference, it has to be the delta. This is the difference. So without the word difference, you're just talking about electric potential at a point, which there is some fine detail that I am about to explain in a little bit. All right. But the key of that one, if I would like to answer that question, I would say no, they are not exactly the same. It seems like the potential difference is just two value of the electric potential subtracting each other. Okay. Okay. They are related, but not the same. Okay. Electric potential is like a single term. Potential difference is two terms. And you want to talk about the difference between them. Okay. All right, cool. Now, all right, it will be a little bit clearer very soon, very soon. All right. So I think I have two questions that I have to answer yours, I think. All right. Okay. All right. Okay. Very good. Getting there. Yeah. Now let's test your understanding so far. Now, because electric field can point in any direction, it doesn't have to be downward anymore. So let's test with a simple one. Let's say that if electric field is pointing from left to right, and you would like to go from point A to point B, which is now not along the electric field anymore, but it's sort of like diagonal a little bit from A to B. My question is, you guys, if electric field value is given, the vector that connecting between point A and point B are also given, and it's say you're moving it at some angle with the electric field lines over here. What is the potential difference from point A to point B? Woo. What do you think, guys? Point A to B, what will be the potential difference? Well, Adan, start from the top. Just bring me the definition of the electric potential. The change of the potential from point A to point B is a negative E dot ds, and then you just do the summation, right? That's the key point. But for this one, you don't need to do the integration just yet. So what you have over here is going to be E dot ds. ds is just that tiny ds along this path over here. But as you can see, if you remember from the definition of the dot product, it's just going to be E, ds, and cosine theta. You guys with me so far? Every time you do the dot products, A dot B is just AB cosine theta, and the theta is just the angle between the two quantities. And theta is constant over here. It's good. Everything is fine. So all you need to integrate is just E S cosine theta. There you go. And you can put ds right here for now. All right, so far so good. Now I can pull out the constant from this. So let's follow me here. Okay, I think you can forget this one for now. Just follow me down here. So negative here, E is constant. Cosine theta is also constant. So all you have left to integrate is just that tiny ds over there. But there's nothing more to it. When you sum the ds, what you get is just the whole length of this, s. So this whole thing gives you back the s. Cool? So that's why at the end, you get the negative es cosine theta. down here. But es cosine theta, when you look at this one, s cosine theta is the d. So it turns out it's a negative ed again. One more time. You done.
Okay.
And does this one look familiar to you? But of course, it has to be, because remember this gravity here? When they bring this mass up to the top of the screen, actually you don't care where on top of my screen. You can move around, along this top portion over here. They're sharing the same potential energy. So that means you can go diagonally, you can go zigzag or whatever. I can throw this mass to you, you throw it back to me, and it ends at the top of the screen. It's still mgh anyway. So what I'm saying over here is you can start anywhere perpendicular to this electric field. All the points on this dashed line over here will sharing the same potential or potential energy. They are the same thing. And now you can move on to this level over here. That will be your difference value of the potential. So that means you can start from A, you can get back to B here, or you can start from A and then you can loop back to wherever on this line here, or you can do zigzag or whatever, and then you end here. The change of the potential will be exactly the same. It's the delta V from A to B. Okay, and just to emphasize one more time, go from A to B is a VB minus VA. I hope this answers your question here. So this is the potential difference. Single term over here, that is your potential. But we are talking about the difference most of the time. So over here at the end, you get a negative ED. Why? Because you start from here. This is high V. This is low V, because, oh, that's log, sorry, low V, because you're going along the field. See, A is upstream. It's sort of like, you're going toward the source of the E, and then you move to your right. That's going along the fields. Every time you move along the fields, you are moving in the direction that's lower your potential or potential energy. They are the same thing.
Okay.
All right. Very good. I mean, it's just like scripting, man. Your question is just perfect to the lecture over here. So what I'm talking about over here is, it means finding out the potential difference doesn't need to worry about the path that taking the, I mean, you don't have to take anything, right? It's just potential difference. So that means when you want to talk about the difference between 2 points, your analysis can be in any format of the path. It can be a straight line, it can be a curved line, it can be a zigzag. It doesn't matter. It's path independent. And this is a property of the conservative force. The force that we are talking about over here is electric force. And electric force is conservative, just like gravitational force. So that's why when I move my mass up, I don't care which path I'm moving up. I don't care. As long as I know the starting point, I know the end point, I know the potential difference. Same thing with the electric field, because we define everything just identically. They're all the same. Okay, so that was the first part that I actually didn't really dive into detail first, because I want to explain about the electric potential and potential energy first. So electric force is conservative force. So that's why you only care about the initial position and the final positions. You don't have to worry about the path, because it's independence of path, taking your system from one configuration to the other. Cool?
Okay.
All right, that's why it makes the energy analysis so simple to use, because you only care about your starting point and your end point. You don't have to worry about how you bring your system from first point to the second point at all. Nice. All right. So I think that's give you a very good introduction of, I mean, it's not even introduction. It's like a proper definition of the potential and potential energy. All right. Now come back to this. I can categorize the problems in potential and electric field into 2 classes, or into categories. The first one is the one that we have already discussed. The electric field has already been given to you. You know the field is pointing up, pointing down, pointing left, pointing right, doesn't matter, that's already given. But we have already seen from previous exercises that you have to deal with the point charges as well. So my question is, what is going to be the potential away from a point charge, or maybe a bunch of charges? Here, for example, if you have a Q charge waiting over here, and you are sitting at, let's say, point A, and you want to move to another point B, what will be the potential difference? See, so this one
Okay.
is going to be exactly just like you asked me before, like, hey, can we do that with the gravity? Yeah. So imagine that this is the mass M, and now you have to zoom out a little bit. So now you're sort of like outside the Earth atmosphere a little bit. So you sort of like floating in the space. So you want to move from point A to point B, and you have some effects due to the mass or maybe some planets, gravitational fields, on and on. You do the exact same calculation over here. Cool. All right. And then you get exact same equation at the end, replacing the charge with the mass M. Okay. Would that answer your question here? Yeah. So the Newton's gravitational law will look exactly the same as this one. All right. So what do you want over here is, now I don't want to dive into detail on this one, guys, because I used to do it. We have to spend like half an hour explaining this whole thing, because you are applying the calculations, which is a vector integral over here, but it's in a spherical coordinates. And some of you sort of like get stuck with that, and then you confused about the R hat already gave us some headache a little bit. So now you have to do some dot product with the R hat, with the displacement. And it's just crazy. All right, I'll just quote the end result. If you want to go from A, you want to NZ B, and A is at distance R sub A from the point charge Q, and at B is at distance RB. It turns out, here we go, guys, the potential difference between A to B, so it's going to be VB minus VA, is this one here, guys. Take it.
Okay.
So it turns out, after your integration, starting from that definition of the potential difference, just the negative integral E dot ds, but you do everything in spherical coordinates and all this stuff. And you apply Coulomb's law, KQ over R squared. What you get at the end is KQ over RB minus KQ over RA. And that's suggesting, if you want, this form over here, KQ over R, can be assigned to be potential at a point, if you want, right there. Hence the formula, I don't know, some of you probably have seen this formula back in the high school physics. It's a KQ over R. But one thing that I want to comment over here is, now you see, every time that you want to use this equation, it seems like the delta just disappears. And you can treat this one as a potential at a point. But in reality, this means you already taken RA to be at infinity. Does that make sense? So I'm saying, every time that you deal with potential, it's just like you have to deal with the potential difference all the time. Usually there's no like a potential at a point. So that means what you're looking at this point right now is just saying that you treat RA to be like far, far away. And then you pretty much like take the difference between point B and that infinity. And this one go to zero. Okay, so that's why every time that you have this formula in use, KQ over R, that always imply that we take V to be zero when R going to infinity. Cool?
Okay.
Just so you know, right? It's annoying. The reason it's annoying because it's by definition, that's what it is. But at least now we understand what the KQ over R means. It just means that you can figure out the potential at a point, but this one is in reference to the point at infinity. Okay, you take potential to be zero at infinity. So it's sort of like, nice thing is it's automatic. Unlike the gravitational potential energy that you calculated before, you have to draw the line, right? You say, okay, Ajahn, I'll take the bottom of the screen to be my zero height, and then you measure the height from that, positive height, negative height, on and on. And some of your friends come in and go, okay, I don't want to use that one. I want to use the top of the screen to be my zero height. And then down here is the negative height. When you have to go over the top, that is positive. So in general, you can set any level, any point, or any place to be your zero potential, because every time that you do the calculation, it's the potential difference. So you can set zero at any point. The difference stays the same. But to be sort of like make it convenient, if we have this setting, so it's sort of like automatic. If you want to use this formula, KQ over R, zero potential is appearing at infinity. It's automatic included. So sounds good.
Okay.
Right. It's annoying, I know, but I mean, if you don't worry too much about anything, this formula works. All right, guys. So that's good. So let's give you a conclusion that you always gonna see this word so many times in the problems. Take potential to be zero at infinity, but the property of the conservative force of the electric field still is there. So that means if you start from one radius and you want to move on to another radius, you don't have to care about the path. You can change from point to point in wherever you like, or you can even just go crazy and come back to this. All you care about is what is the starting radius A and what is going to be the final radius B. And that's it. That's all you care about. Okay. So everything works just like before. Okay, cool. Nice. So just to be complete in terms of the contents. So once we complete this one, then we don't have to worry about defining this and that anymore. So if you take that V equal to KQ over R to be the formula for you to calculate a potential relative to infinity, of course. And now if you have like continuous charge distribution instead of like a point charges lying around, you just use the same technique that you did before back in the day of the electric field. You do the slicing, chop, 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 chop thing, and then you say, okay, within that slice, you have dq contained in it, and you can start calculating the potential from that. You just say, okay, Dan, the potential over here is going to be k dq over r. But because your charge is going to be small, you're going to call it like a meet potential here. And if you want them all, you just do like another dq, another dq there, another dq there, another dq there, and every dq will contribute dv to the point P. So you want all of the contributions for all the dq, all you have to do just do the integral and you are done.
Okay.
Okay. So you say, John, are you gonna have to deal with calculus again? Well, yeah. But the good thing about this one is there's no more vector summation. So the good thing about this one is it's just the number summing. So that means you have to take positive and negative charge into account. Just like level, you can go above the reference point or you can go below. So you have positive and negative potential. Same thing over here. Okay, so that's the difference. You don't have to worry about the directions anymore. The only thing is you just have to take care of the sign properly, but it's just an algebraic sum. So complication will be a lot less than before. All right, that's a good sign. Okay, all right. So, I mean, but don't worry about the calculus at this point because we're not going to do that today. All right, we're just going to sort of like build up your confidence in terms of how to solve this thing one by one, and then hopefully it will get a lot better toward the end. So let's do a couple of exercises today, just warm things up, and then I think we can finish all the topics and everything about the potential next time. Okay, so it won't be too much for you in a day. All right, I think we already had too much in the morning here. All right, guys, so let's try this. The figure shows four arrangements of charged particle, all at the same distance from the origin. So let me name that distance to be like A, then yeah, why not? Yeah, so that's just A as well. So it ranks these situations according to net electric potential at the origin, most positive first, taking potential to be zero at infinity. See that? So every time that you see this clause or this sentence over here, that means you have a ticket and you have the permission to use KQ over R. So that's kind of nice.
Okay.
All right, cool. So that's good. We're going to use that KQ over R to calculate. So let's start from the first one, shall we, guys? So let's look at A. So let me call this like a sigma V in the case A here. So you have two charge over here. You have positive 2Q and negative 9Q here. So what you have to do, just do it one at a time. So it's going to be K plus 2Q. See, I have to bring in the positive charge. The positive sign has to be in it as well. K plus 2Q divided by the distance from plus 2Q to origin here is A. Don't need to square it. And that's it. You're done for the first one. Now you add the second contribution from the negative 9Q and the same distance here. And that's it, guys. Just add these two together and you are done. It's going to be, I can pull out a common factor and then I have negative 7Q. That's it.
Okay.
I think you like that. Try again, shall we? What about the second one? Part B. All right. The total potential at point B is going to be what? Well done. Now it's easy. Let's start with the negative 2q divided by A plus negative 3q, K negative 3q over A. Whoa, it's done again. I pull out the common factor and add this negative 2, negative 3, and negative 5q. You are done.
Okay.
Whoa, is that easy? Yeah, it is that easy. All right. And now you start to see about that. If now you have 4 charges and they are at the same distance from the point that you would like to calculate the potential, you're going to get the same common factor K over A. So and now I start to see, okay, I can shortcut this a little bit now. They're all going to have K over A factor. So all you need to do is actually just summing all those charges at the same distance, right? Why not?
Okay.
So what you have here is negative 2, negative 2, negative 2, negative 1. So it's total of negative 7q. And that's it. You're done right away. See, make things a lot easier. Same thing with the last one. You have negative 4 plus 2, negative 7 plus 2. So the total potential at at the origin in the case D is going to be K over A, common factors. And you just sum all the charges over here. And that is negative 7q as well. And from the look of this one, well done. All right, that's easy to see. The highest one is this dude over here. It's negative 5.
Okay.
That's the most positive. And the rest are the 3 cases sharing the same K negative 7q over A. And you are done.
Okay.
See? So I hope by showing you this, you see how simple it is for you to calculate the electric potential. It's just algebra. No more vector, no more directions. Things are easier now. Yeah, try again, guys. Last one of the day. Sounds like a good plan.
Okay.
All right. So in the figure, you have 8 particles form a square with distance d between adjacent particles. Okay, cool. Everything is good. With the what is the electric potential at point P at the center of the square if electric potential is 0 at infinity? See, you see this sentence again. So when you see this one, that's your ticket to using KQ over R. Check. Good. Go for it. All right. So I'm going to start from the upper left corner, shall we? All right. So this minus 4Q will give the contribution to the electric potential at point P. Now you can figure out the distance there, which is not too bad. If this is D, this is also D. That is going to be root 2D. You guys with me? Cool. So let's do that. So the net potential at point P is going to come from, start from that K minus 4Q over the separation or the distance from that charge to the point of calculation. That's it, guys. That's done for the first one. All right, move on to the next. Let's go negative 2Q. Now the distance from that one is just going to be just D. Oh, yeah, cool. So I'm going to do that. So plus K minus 2Q, don't forget the sign because sign is important here, divided by, now the separation is only D. Done. And now just repeat the process here. So move on to the next. At the upper right corner, you're going to have the contribution to that point P of, let me just say once again, plus K plus Q over separation is root 2D again. And you just keep going. All right, get to the next, minus 5Q. It's going to give some contribution a little bit there. So you say, Ajahn, no big deal. It's going to be K minus 5Q over D. And now when you do a little bit, a couple of terms, and then you start to see about that, wait a second. You either have the charge at the corner, 4 of them here, and you have 4 more on the side. So the first group, those charges at the corner will share the same common factor of K over root 2D. Yeah, you saw that one, right? You saw that one, like you practiced from these previous problems a little bit here. So And the charges on the side will share the common factor of K over D. Well, Dan, why don't you just sort of like do it like one group at a time? So let's do that. So what I know right away is if you keep doing this, the charge at the corner will have root 2D and K over root 2D as a common factor. And all you need to do is just sum all the charges at the corner actually, right? With me? So actually, why don't you jump straight to the result? So you're gonna get, okay, let me erase that positive sign there. So all the contribution from the corner charges is gonna be K over root 2D, and then you can take minus 4Q plus Q plus 4Q minus Q. You guys with me? 1, 2, 3, 4. And the good thing about this one is, well, whoa, then this one go to 0. See, it's much faster.
Okay.
At least, all right, it's just like, well, if you sort of like observe and say, oh, okay, I can quickly calculate this very easily by just taking the charge summation, and then you can jump right into the conclusion that there will be 0 contribution from the corner charges. Nice. So the only thing left for you to do is just the contribution from the charge on the side. You have common factor of K over A. And now just take the charge on the side and do the summation there. It's going to be minus 2Q, minus 5Q, minus 2Q again, and plus 5Q. So the good thing is it's like easy cancellation over here. And then at the end, the net potential at point P is going to be negative 4KQ over A. D, sorry, over D. There, just say A, sorry. Yeah. And you are done right there.
Okay.
Cool. All right. So at least this gives you a hint of what's about to happen for electric potential. It's just numerical numbers. There's no directions. So it make summation or integral a little bit easier for you to calculate. Sounds like fun? All right. And I think this is it for today, guys. I think you have enough introduction to the electric potential and electric potential energy. Next time we'll do more complicated and plus, of course, calculus-based problem too. Okay, sounds fun. All right, guys. So any the questions or anything? All right, if not, that is it for today, guys. I'll see you guys next week. Thank you so much. Bye-bye.